All right, so what I want to do is talk a little bit about linear functions, things that they might model and why we care about them, what their unique characteristics are, and then the mathematical formulas that we need to be familiar with and flexible with in order to apply them and analyze them. So a lot of this should be review. Linear functions are something that's talked about pretty early on in algebra. And so for advanced algebra, this is a bit of a review. And so many of these things, hopefully you've seen before, and we will practice with them during our synchronous classes. So I'm just choosing my utensil right now, what I'm going to write with. But the first question we might ask is, what is a linear function? And perhaps why do we care? Okay, so I thought of a couple examples really quickly off the top of my head. One is if you are an hourly worker, usually you are paid the same amount per hour. And we actually saw an example of that with direct variation. Direct variation is, or at least y equals kx, is a type of linear function. So I wrote down the scenario. If for every hour you work, you are paid $15, that would be a linear function. So I'm going to just type this in here. Suppose you are paid $15 for every hour that you work. So in that case, every additional hour gives you an additional $15. 2 hours would give you $30. 3 hours would give you $45. But each additional hour, the important thing is giving you that extra $15. So basically what we have here is we have a scenario that demonstrates a constant rate of change. Constant rate of change. And that is really the most important thing about linear functions. They have a constant rate of change. And so in this case, it would be $15 per hour. That's how much you're getting paid to do that hourly work. And of course, we could have a whole discussion about minimum wage and whether that should be higher and how that might benefit some of the individuals that do a lot of the essential work that our society depends on. Another thing I was imagining is suppose you are hiking up a mountain. I know I love to hike. And usually it gets cooler as you go up. Now, I'm not sure this is necessarily linear. In fact, it's probably not. But we could suppose a scenario, right? Suppose that for every 1,000 feet of elevation gain, the temperature decreases by 3 degrees. So this is probably not true. I don't really know. That would be an interesting question. As you move higher, does the temperature decrease at a constant rate of change? I don't know. I would guess perhaps not, but it's possible, I suppose. And so again, this is a constant rate of change scenario where we might say, well, as you gain 1,000 feet, your temperature decreases by 3 degrees. So that is -3 degrees over 1,000 feet. Or if we simplified this, we would get -0.003 degrees per foot. Okay, so again, that would be a constant rate of change. Maybe you started at 60 degrees, and then as you move up 1,000 feet, you're now at 57. And as you move up another 1,000 feet, you are now at 54, etc. And each foot, theoretically, your temperature is going down by 0.003 degrees, which is obviously not very much. And that makes sense because the difference in the temperature shouldn't be huge, probably. I don't know if this is a reasonable scenario. It's just something I made up. So we care about linear functions Here, we might think of a linear function that's something like y equals 15 times x, or maybe in function notation, we might write f of x is equal to 15x, or we might even write f of t is equal to 15t, right? Where t is giving you the number of hours that you work, and f of t is giving you how much you are paid. Over here, we might write in function notation, we've got temperature as a function of height, so maybe t of h, or maybe altitude, so t of a is equal to, well, again, let's suppose that at sea level, it was 60 degrees. So that would be like my y-intercept. And then I could subtract 0.003 times a. So we might even write this as negative 0.003a plus 60. So you'll see this sort of mx plus b. In this case, you're not paid anything if you don't do any work. So the y-intercept is 0. And here's this mx plus b. Of course, my variables are changing. But that is the idea of a linear function. You've got some starting amount, whether it's 0 because you haven't worked and you're not getting paid, or maybe at sea level it's 60 degrees. And then something is increasing or decreasing at a constant rate. So we've got a constant rate of change. So there's lots of things that have this constant rate of change relationship, which is why we care about linear functions. And this is sort of what's really important about linear functions. Okay, so moving on, let's talk about some of the mathematical formulas that we need. So first of all, we need to know slope-intercept form. So slope-intercept form is given by y equals m times x plus b. So that's the general form. But an example, or two examples, would be y equals negative 2x plus 4. And another example might be y equals 1/2 x minus 6, let's say. Okay, so these are functions. We could also write them as f of x equals negative 2x plus 4, or we could call this g of x equals 1/2 x minus 6. And let's remind ourselves that 4 and negative 6 are the y-intercepts. And to find a y-intercept, you simply plug in 0. So since f of 0 is negative 2 times 0 plus 4, we get f of 0 equals 4, and that's my y-intercept for that function, 0, 4. So this is the y-intercept. Over here, g of 0, if I plug 0, remember 0 is the x value along the y-axis. So g of 0 would be 1/2 times 0 minus 6, which is just negative 6. So that is the point 0, negative 6. So you can see that that is again, the y-intercept. And so b, that is the y-intercept. 0 comma b would be the y-intercept. So that's like our starting value. So maybe our starting temperature, maybe the amount that we're paid just for showing up to work. Who knows? That's our starting amount, usually, is the y-intercept. And in algebra and mathematics, the y-intercept is one of, not that many things that are really important to be able to find. So you definitely want to know. To find a y-intercept, I can simply plug in 0. And in this case, I know that I will just get b. Now, if I make some tables here, so let's make some tables. Let's make a table for, let's see here, I'm doing blue right now. So let's make a table for g, that's going to be blue, so x and g of x. And let's make a table for f, that is going to be red. So here's x and here's f of x. So it's good to maybe plug in some numbers close to 0 that aren't too challenging. So let's plug in, say, -2, -1, 0, 1, and 2. So if I plug -2 in right there, I get -2 times -2 plus 4, which is 8. If I plug -1 in, I get -2 times -1 plus 4, 4, 5, 6, which is 6. If I plug 0 in, I get 4. If I plug 1 in, I'm going to get 2. And if I plug 2 in, I am going to get 0. So my outputs are 8, 6, 4, 2, 0. So you can see that these values are decreasing. From 8 to 6 was -2. From 6 to 4 was -2. From 4 to 2 was -2. From 2 to 0 was -2. This is my change in y. Change in y. And over here, my x values are increasing. From -2 to -1 is +1. From -1 to 0 is +1. From 0 to 1 is +1. And from 1 to 2 is +1. So this is my change in x. My change in x. And I can tell that this is a linear function because those changes are constant. More specifically, more precisely, the ratio of those changes is constant. So you see that -2 divided by 1 is -2. -2 divided by 1, -2. -2 divided by 1 is -2. And so that right there is my slope, or rate of change. And in this case, it is -2. Now, if I did the same thing with g of x, and maybe you want to pause this video and do it without me, but let's say we plug in -2, -1, 0, 1, and 2. So plugging those into g of x, if I plug in -2 times 1/2, so 1/2 times -2 minus 6 is, let's see here, that's going to be 1 minus 6 is -5. If I plug in -1, I'm going to get wait, is this right? -2. Oh, it's positive 1/2. Whoopsies. So that means that I'm going to get 1/2 times -2, that's -1 minus 6, that's -7. When I plug in -1, I'll get -1/2 minus 6, that's -6.5. Plug in 0, I get -6, that's what I already found over here. Plug in 1, I'm going to get -5.5. And plugging in 2, I'm going to get -5. So you can see my change in my y values here. Each time I am adding 0.5. And for x, each time I am adding 1. So if I take the ratio of those two, 0.5 divided by 1, I should just get 0.5 or 1/2. And again, that right there is my slope. That's my rate of change. So I know that this right here, the m value, that's just a number. So in this case, -2, in this case, 1/2, that is my slope, or constant rate of change. Okay, so there's a lot on this screen right now, but what I want to communicate finally is that if you have y equals mx plus b, that is a linear function with slope of m and y-intercept of 0, b. I like to write it as 0, b because that reminds me that it's an actual point. Okay, so we define slope, of course, m to be change in y divided by change in x, or the rate of change, how quickly y is changing with respect to x. So I'm going to write that down here. How quickly y is changing with respect to x. And this is a constant rate of change in this case. And we sometimes say it could just be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So that is my slope formula, we call it, which you've probably seen before, which finds the change in y and divides it by the change in x, and that gives me how quickly y is changing with respect to x. So miles per hour, or degrees Fahrenheit per foot, or dollars per hour. So this is how you find your slope. Okay. So for instance, as a quick example here, let's say you had the 2 points, 2, 4, and let's say -1, 3. So if you wanted to find the equation between these 2 points, you could first find the slope, which is change in y over change in x. And so let's call this x2, y2, and this x1, y1. So now that would be 3 minus 4 divided by -1 minus 2, which is -1 over -3, or 1/3. That is the slope. That's the constant rate of change. And then I could say, great, y equals mx plus b, but I know that my m is 1/3, so y equals 1/3 x plus b. Now I'm going to go to the next page. So I've got y equals 1/3 x plus b, but what is b? How do I find that? Well, what I could do is plug in a value for x and y and solve. So coming back here, why don't I choose the 2, 4, and I can basically plug in 4 for y and 2 for x and find my b value. So I'd get 4 equals 2/3 plus b, and subtracting 2/3, let's see, 4 is 12/3. Subtracting 2/3, I should get 10/3 equals b. And so I could finally write my equation as y equals 1/3 x plus 10/3. Okay, so that's all fine and good. But what made this a little bit more complicated was, I found my slope and then I had to solve for b, and that was kind of a pain. So when you have 2 points, or you have a slope and a point, there's another form of the line that we use. And so I am going to write that right here, because this is a pretty important takeaway. When you have 2 points, or when you have the slope and a random point, so not the y-intercept, although it works with the y-intercept as well, then you may use the point slope form of a line to write the equation. And so this is kind of a nice form because it works for any point and a slope. So if you have the slope and you have a point, any point, let's call it x1, y1, then the equation of the line, point slope form of the line, so for any point and the slope, is written y minus y sub 1 equals m times x minus x sub 1. And so for this example, we had the slope of 1/3, great. We had a point 2, 4, so we can just say, so we had the point 2, 4, and we had the slope 1/3. So we can just say, great, that would be y minus 4 equals 1/3 times x minus 2. This is another way to write the same equation. I'm not sure that notation right there with the 3 lines is correct, but these two are the same line. If you graph them, they will look the same. If I solve for y on the right-hand side, I will get the same equation. Okay, so to summarize, so far, what we have is we have y equals mx plus b, y-intercept and slope. We have y minus y sub 1 equals m times x minus x sub 1. Remember, y and x are your variables. Those are the things that are going to stay in the equation, because in order to have an equation, we have to have an input, we can plug something in, and an output. So that would be x and y. x1, y1 is just a point. That is a specific point, like 2, 3, or -5, pi. These are specific points. Okay, and m, of course, is equal to y2 minus y1 over x2 minus x1, which is the rate of change or the slope of the line. And the final thing that we're going to use a little bit later is standard form. This one isn't used maybe quite as much, but standard form for a line is often written ax plus by is equal to c. So that one's not great for writing the equation. It's not great because I don't know what the slope is, and I don't know what a point is on the line, and I don't know what the y-intercept of the line is, but it is useful for when we solve systems of equations using a linear combination, aka elimination. So standard form is used for some things, but not as much as your heavy hitters up here, which would be slope, intercept, and point slope. Okay? So the final thing I will do here is just look at a couple examples. So let's take an example where we have, say, the point -2, 3, and the point 0, 5. Okay? So if we wanted to find the slope between these 2 points, we could use the slope formula, m equals y2 minus y1 over x2 minus x1. I like to label these points as x sub 1, y sub 1, and x sub 2, y sub 2, so I don't make any mistakes. So this would be, it doesn't matter which is which, by the way. I just arbitrarily chose it that way. 5 minus 3 over 0 minus a -2, which would be 2 over 2, which is 1. So it looks like my slope is 1. Then I could use my formula y minus y sub 1 equals m times x minus x sub 1, which is point slope form. PS. Yay. And I can write that now as y minus 3 equals m, which is 1 times x minus a -2. And so that would be y minus 3 equals x plus 2, or y equals x plus 5. So that would be my equation. And it makes sense because here the y-intercept is 0, 5, and that is what I saw up here as well. So it makes sense that my y-intercept would be 5. That matches what I had. And remember that there are many different ways to graph, but one way is to just plot these 2 points. So here's -2, 3, right there, and 0, 5. 0, 5 is here, and simply connect the dots. Another way is to plot the y-intercept at 0, 5, then move up 1 and over 1 because that's my slope, and then connect those 2 dots. So I can see that this is an increasing linear function with a slope of 1 and a y-intercept of 5. So we need to do some practice with these, find the equations, graph the equations, apply the functions, think about maybe parallel lines, right? What does it mean for our lines to be parallel? What about perpendicular? You know, what might be the equation of a vertical line, right? You know, what do we call this? And hopefully you're remembering, wait a second, isn't that just, you know, x equals 2? And what do we call a, you know, horizontal line right here? And you're like, well, isn't that just y equals 3. And so there's some other things to think about here, but that should be a great start on what you need to know. And so I guess to summarize, what you really want to know is slope, intercept, form. Make sure you know that. Point, slope, form. Make sure you know that. The slope formula. Make sure you know that. What is a y-intercept and how do you find it? You want to know that. What does it mean to have a constant rate of change? Definitely want to know that. Think about increasing versus decreasing. Definitely want to know that. So these are the things that you kind of want to have summarized in your notes. All right. I think that's it. So until next time, stay classy, diligent. I don't know. See you later.